124 light-years from Earth, a planet larger than ours floats around a small red star. The James Webb Space Telescope just looked at it and saw something terrifying. A chemical signal flickered in its atmosphere, and on Earth, only one thing makes that chemical: living organisms. We're going to take you to a possible alien ocean, into a hydrogen sky, past a strange missing molecule that has scientists arguing, and into the moment Webb crossed a line no telescope ever has. If this fascinates you as much as it does us, hit subscribe so you never miss what we find next. Get ready. We begin. It was a quiet evening at the University of Cambridge when Niku Madhusudhan opened a fresh batch of data from the James Webb Space Telescope. He had been waiting for these numbers for months. His team had pointed the most powerful space telescope ever built at a single dim point of light, 124 light-years away, and asked it to do something almost impossible. They wanted Webb to read the air of an alien world. What came back made his hands go cold. In the long stream of data, a strange shape appeared. A dip in the starlight, a fingerprint. The kind of fingerprint left behind by a molecule called dimethyl sulfide. On Earth, that molecule has only one known maker. Not lightning, not volcanoes, not ice, life. Specifically, tiny ocean creatures called phytoplankton, the green dust of the sea. For a long moment, he just stared at the screen. If the reading was real, this was the strongest hint of life beyond our solar system that any human had ever seen. Not a rumor, not a guess. A measurable signal pulled from the air of a planet so far away that its starlight took more than a century to reach us. He called his team. They double-checked the numbers. Then they checked them again. The signal held. The math gave them 99.7% confidence that something in the atmosphere of that distant world was making this chemical. In science, that number is huge. In daily life, it sounds like certainty. But in the search for alien life, it is not enough. Not yet. Because here is the strange part. There is one other possibility. A possibility nobody can rule out. Something hiding inside the data that could either prove life exists or quietly destroy the entire claim. The planet they were studying has a name that sounds like a code from a spy movie. K218b. It is not a small rocky world like ours. It is bigger, heavier, and wrapped in a thick blanket of hydrogen gas. Some scientists think a vast ocean rolls beneath that blanket. Others think the surface is so hot that any water would turn into a screaming cloud of steam. Either way, something on that planet is producing a chemical that, here on Earth, only living things make. The team spent weeks preparing the announcement. They knew what would happen the moment they pressed publish. Reporters would call. Headlines would scream. People who had spent their whole lives wondering if we were alone would finally have a real reason to hope. And critics would line up, ready to tear the work apart molecule by molecule. When the paper finally went public in April of last year, the reaction was exactly what they expected. Some called it the most important detection in the history of astronomy. Others called it a mistake waiting to be exposed. Both sides had reasons. Both sides had data. And both sides agreed on one thing. This single planet, this single signal, this single point of light in the constellation Leo had become the most important target in the entire night sky. But to understand why this signal matters so much, we need to leave Earth completely. We need to travel to K218b itself and look at what kind of world is actually waiting on the other end of that beam of starlight. If you could climb into a starship and fly to K218b, the trip would take you longer than human civilization has existed. At the speed of light, you would travel for 124 years. In a real spacecraft, you would travel for millions. When you finally arrived, nothing about the place would feel familiar. K218b is what astronomers call a sub-Neptune. That single word hides something weird. It means the planet is bigger than Earth, but smaller than Neptune. There is nothing like it in our solar system. We have small, rocky worlds. We have giant gas worlds. We have nothing in between. Yet, across the galaxy, sub-Neptunes are the most common kind of planet we have found. Our solar system, it turns out, is the strange one. This particular sub-Neptune is about 2.5 times wider than Earth. That sounds modest until you do the math. Volume grows fast when a planet gets bigger. K2-18b is roughly 8 times more massive than our home. If you stood on its surface, assuming you could, gravity would pin you down with a force you could barely fight against. Every step would feel like carrying another version of yourself on your back. The surface itself is a mystery. We do not know what it looks like. We may never know. The planet is wrapped in a thick atmosphere of hydrogen gas, and that hydrogen blocks our view like a fog that never lifts. Webb cannot see through it directly. It can only read what is mixed inside it. But that mix has stunned scientists. Inside that hydrogen blanket, Webb has spotted methane. It has spotted carbon dioxide. It has spotted water vapor. And now, possibly, dimethyl sulfide. Each of those molecules tells a piece of the story. Together, they paint a picture that should not exist. A normal sub-Neptune is supposed to be a small, failed gas giant, a miniature Jupiter, hostile, crushed, and lifeless. But K2-18b does not look like that. The gases inside its air match a much stranger model. A model where the planet has a deep ocean of liquid water hiding under its hydrogen sky. If that ocean exists, it would be unlike any ocean ever imagined. The water would not lap against beaches. There would be no beaches. There might not even be a solid floor below. Just water going down for hundreds of miles, getting hotter and stranger the deeper you fell. Above the surface, no blue sky. The hydrogen would scatter light differently, possibly painting the heavens a dull pink or murky orange. And yet, somewhere in that alien setup, something might be alive. The planet sits in what astronomers call the habitable zone of its star. That is the narrow ring of distance where water can stay liquid, not too hot, not too cold. The conditions on paper allow life. Whether life actually took the chance is the question that has consumed thousands of scientists for the last several years. Even more unsettling, K2-18b is not floating in normal sunlight. It orbits a small, angry kind of star that behaves very differently from our calm yellow Sunday. That star throws tantrums. It blasts the planet with radiation in violent flares. That detail alone could decide whether anything down there survived. And that is exactly where we are going next. The star that warms K2-18b is not a star like ours. It is smaller, dimmer, and colored a deep, moody red. Astronomers call it a red dwarf. In the galaxy, red dwarfs are not rare. They are the most common type of star we have ever found. 3 out of every 4 stars you can imagine in the Milky Way are one of these little red ones. Our yellow sun is the unusual one. But common does not mean kind. Red dwarfs are tiny in size, sometimes less than half the width of our sun, and they burn far cooler. Their light is weaker, their warmth is gentler. To get any heat at all, a planet must orbit very close to one. K2-18b sits so near its star that a single year on this world lasts only about 33 Earth days. Imagine your birthday arriving every month. Imagine the seasons, if there are any, racing past in weeks. That closeness comes with a price. When a planet hugs its star tightly, the star's gravity grips the planet hard. After millions of years, that grip can lock the planet in place. One side ends up always facing the star, baking in eternal day. The other side ends up frozen in eternal night. There is no sunrise, no sunset, just a fixed wall of light on one half and a fixed sheet of darkness on the other. Scientists are not sure yet if K2-18b has been locked like this. The hydrogen sky might mix the heat around enough to keep things even. But if it is locked, the planet would be split into 2 extreme zones, with a thin twilight ring running between them. That ring, where day meets night forever, is exactly the place where some researchers think life would be most possible. There is another problem with red dwarfs. They are violent. These small stars often throw out huge bursts of energy, called flares. The bursts can be hundreds of times stronger than anything our sun produces. A planet sitting close to a red dwarf gets hit by these flares again and again. Radiation slams into its atmosphere. Charged particles strip away the upper layers. Over millions of years, smaller, weaker planets can lose their air entirely. They end up bare, dead, and burned. K2-18b has so far survived. Its hydrogen blanket is still there. Webb measured it. That alone is good news. The planet has held onto its atmosphere despite living next to a moody, flare-prone neighbor. But scientists do not yet know how much radiation has reached the surface, or whether anything below could shield itself. This is where the deep ocean theory becomes interesting. Water is one of the best radiation shields known to physics. Even a few feet of liquid water can absorb dangerous rays before they reach anything below. If K2-18b really does hold a global ocean under its sky, then any tiny life forms swimming a short distance below the surface would be protected, hidden, safe. That setup paints a quiet, almost peaceful picture. A hidden world dimly lit by a red sun, sheltering its delicate residents inside dark water while flares rage above. It is a beautiful idea. It is also a hard idea to prove, because to prove anything about a planet that distant, scientists had to invent a way to see something that should be invisible, a way to read the air of a world that no human will ever touch. To understand what Webb actually did, picture this: a flashlight, a bottle of perfume, and a piece of paper. Now turn the flashlight on and shine it through the perfume bottle onto the paper. The light passes through, but something changes. The chemicals inside the perfume soak up tiny pieces of that light. Different chemicals soak up different colors. By looking at exactly which colors are missing, you can figure out what was in the bottle, even if you never opened it. That is, more or less, what astronomers do with planets. The flashlight is the star. The bottle is the planet's atmosphere. The paper is the camera inside the James Webb Space Telescope. When K2-18b passes between us and its star, a sliver of that starlight slips through the planet's outer air. The molecules in the atmosphere grab certain colors. By the time the light reaches Webb, those colors have small dents in them. The dents are tiny. They are heartbreakingly tiny, but they are there. Each molecule leaves a different pattern of dents. Water leaves one, carbon dioxide leaves another, methane has its own, and dimethyl sulfide, the molecule that lit up the headlines, leaves a fingerprint of its own that no other common chemical exactly copies. The only way to read these fingerprints is to wait for the planet to pass in front of its star, then catch the brief moment of starlight filtering through its sky. That moment is called a transit. For K2-18b, a transit lasts only a few hours. Then the planet swings around the back of the star, and the chance is gone until the next orbit. Webb has caught these transits multiple times. It uses different cameras to break the light into hundreds of color bands. Then computers compare the patterns to a giant library of known molecules. If the match is good, scientists can claim a detection. The first detection on K2-18b came in 2023. Webb spotted methane and carbon dioxide in clear, strong amounts. That alone was big news. It meant the air of this distant planet was nothing like the empty hydrogen shell most people expected. There was real chemistry happening up there. But buried in that 2023 data, there was a faint, ghostly hint of something else. A whisper in the spectrum. The shape almost matched dimethyl sulfide. The signal was too weak to trust. The team did not say life. They said maybe. That whisper was enough to make them ask for more time on Webb. They wanted a different camera, looking at a different range of colors to test the same patch of sky again. If the whisper was real, it would show up again, If it was just noise, it would vanish. 2 years later, Webb pointed back at K2-18b, this time with a different instrument. The result was louder. The shape returned. The fingerprint was clearer. The math said only 3 out of every 1,000 random datasets could fake this pattern. That is the famous 99.7%. It sounded like a confirmation. It looked like a confirmation. But the deeper anyone looked at the chemistry of dimethyl sulfide, the stranger the story became. Because to truly understand what this molecule means, you have to see what it does back on Earth. If you have ever walked along the seashore and smelled that sharp, slightly sweet scent that hits you when the wind blows in off the waves, you have already met dimethyl sulfide. Most people call that the smell of the ocean. Scientists call it the smell of life. It is not the salt you are smelling. Salt has no scent. It is not the sand. It is not the seaweed exactly. It is a gas made by trillions of tiny green creatures floating just below the surface of the water. They are called phytoplankton. Each one is microscopic. Together, they cover huge stretches of every ocean on Earth. Phytoplankton drift in sunlight, soak up carbon dioxide, and produce oxygen, just like land plants. About half the oxygen you breathe comes from them. They are the quiet engine of the planet, and as part of their daily chemistry, they release a chemical called dimethyl sulfide into the air. The amount is staggering. Earth's oceans pump millions of tons of this gas into the sky every year. It rises, mixes into clouds, and even helps shape weather systems. Without these tiny creatures, the smell of the sea would not exist. Some seabirds even use the scent as a map. They follow plumes of dimethyl sulfide through the open ocean to find patches where food is plentiful. Here is the part that matters for K2-18b. After more than 100 years of chemistry research, scientists have only ever found one reliable, large-scale source of this gas on Earth: living organisms. Volcanoes do not make it in any meaningful amount. Lightning does not produce it. Ordinary atmospheric chemistry does not cook it up out of nothing. There are tiny non-living sources, but they are weak, slow, and short-lived. To fill an entire atmosphere with the stuff, you need life. On our planet, you need oceans full of phytoplankton churning it out day after day. That is the entire reason scientists were so shaken when Webb saw the same fingerprint in the air of an alien world. Even more striking, the amount detected on K2-18b appears huge. The data suggests levels of dimethyl sulfide thousands of times higher than what Earth's oceans produce. If the signal is real, that planet is not just barely making it, it is drowning in it. Imagine an ocean so thick with microscopic life that the air above it reeks of biology 100 miles up. That image is exciting. It is also exactly the kind of claim that makes other scientists nervous. Because when something seems too good, the universe usually has a twist hiding somewhere. The first twist appeared right away. Critics asked a fair question. If Earth is the only place we know that makes this molecule, how can we be sure it is impossible to make it any other way? Maybe in a hydrogen-rich sky, with strange chemistry no one on Earth has tested, dimethyl sulfide forms on its own. Maybe a comet rich in sulfur could deliver it. Maybe there is a process nobody has thought of yet. These are not dismissive questions. They are the right questions, and nobody yet has clean answers. So before any team can stand up and say we have found life, they have to walk back through every twist and every doubt. The story of how that walk back began starts a couple of years before the famous announcement, in a much quieter moment. 2 years before the headlines, Niku Madhusudhan and his team were looking at a different set of Webb data. It was 2023. The James Webb Space Telescope had only been running for about a year. Its cameras were still being tested on real targets. K2-18b was one of the planets on the list. The first round of observations was meant to be simple. Find the basic gases, confirm that the planet had a real atmosphere, see if water was there. The team used Webb's near-infrared cameras to catch the starlight passing through the planet's air during a transit. What they got back was richer than anyone expected. The data clearly showed methane. The signal was strong, with a confidence level scientists call 5 sigma. That means the chance of it being a random accident is less than 1 in a million. Methane in an alien atmosphere is exciting on its own. On Earth, most methane comes from biology: cows, swamps, microbes. There are non-living sources too, but the gas is a known whisper of life. Finding it on K2-18b made the planet immediately interesting. Carbon dioxide showed up at a slightly lower confidence, around 3 sigma, but still clear. That was another big deal. Carbon dioxide and methane together are very hard to keep mixed in the same atmosphere. The two gases tend to react and cancel each other out over time. Finding both at once usually means something is constantly making them. On Earth, that something is, again, life. Hidden inside the same data, the team noticed a strange bump, something at a certain wavelength that did not match methane, did not match carbon dioxide, and did not match water. They ran the numbers. The bump roughly fit dimethyl sulfide, the same molecule the ocean's tiny creatures pump into our skies. But the signal was weak, too weak to trust. The fit was rough. The shape was sloppy. If the team had announced a detection at that level, every other astronomer in the field would have torn the paper apart. They knew that, so they did the careful thing. They mentioned the hint in their paper, called it tentative, and recommended more observations. The science world still reacted strongly. Even a tentative whisper of dimethyl sulfide on a habitable zone planet is news. Articles ran. Discussions began. Skeptics pointed out the weakness of the fit. Supporters pointed out how many big discoveries in history started as faint hints in noisy data. For Madhusudan and his team, the next move was clear. They needed to look again, with a different camera, at a different range of color. A separate test, using Webb's mid-infrared instrument, would either lift the whisper into a real signal or knock it down for good. If the gas was truly there, it should leave fingerprints in that range too. They submitted a new observation request. Webb's schedule is fiercely competitive. Hundreds of teams fight for each hour. But the case was strong. Methane and carbon dioxide were both present in a habitable zone atmosphere. A possible biosignature was hovering on the edge of detection. The committee gave them the time. The wait was almost a year. While they waited, the team studied every possible non-biological way to make dimethyl sulfide in a hydrogen-rich sky. They wanted to be ready to defend or kill their own claim. When the new data finally arrived, the room went silent. What they saw next is exactly what made world headlines. And it pushed the entire question of alien life into a place no scientist had stood before. Out of more than 5,000 known planets beyond our solar system, the team kept returning to one, a faint dot of light in the constellation Leo. They could have chased larger planets, hotter planets, planets that were easier to study. They did not. They chose K2-18b again. The reason is a quiet kind of obsession that runs through every serious scientist. When the universe hands you a strange clue, you do not let it go. K2-18b had been collecting strange clues for years. It was one of the very first planets ever found in the habitable zone of a small star. It was the right size to potentially hold an ocean. It had a hydrogen atmosphere strong enough to read with a telescope. Its star was close enough to deliver bright, clean signals. And now it had a whisper of dimethyl sulfide hanging in its air. In short, the planet checked every box you would draw if you were sketching the perfect target for finding alien life. That kind of luck almost never happens in astronomy. Most planets we discover are too far, too small, too dim, or too hostile to study in detail. K2-18b sat in a sweet spot, so the team made a decision. They would point one of the most expensive machines ever built at this single faint world again, and burn precious hours of telescope time trying to confirm the whisper. But Webb is not just one camera. It carries several instruments, each tuned to see a different part of the light spectrum. The 2023 data had come from the near-infrared instruments. Those tools see colors close to red, just past what human eyes can detect. They are powerful, but they have a limit. Some molecules, including dimethyl sulfide, leave their strongest fingerprints in a different range, a range called the mid-infrared. To catch that range, the team needed to use Webb's MIRI instrument. MIRI is short for mid-infrared instrument. It is the only one of Webb's cameras kept extremely cold, chilled down with a special cooler so it can detect faint heat from very distant objects. MIRI sees in colors so deep they have no name in human language. Using MIRI on a planet as small and far as K2-18b is brutal. The signal coming back is so tiny that even the smallest disturbance, a tiny shake of the telescope, a tiny shift in temperature, can blur the result. Each transit lasts only a few hours, and the team needed several of them. They had to schedule the observations down to the second. A single mistake could waste an entire transit, and they might wait weeks for another chance. Why go through all that? Because if dimethyl sulfide really existed in the atmosphere of K2-18b, MIRI would see it from a completely different angle, a separate camera, different colors, different chemistry. If the same answer came back from two independent looks, the case would jump from a curiosity to a candidate biosignature. If the answer did not come back, the whole story would dissolve. The 2023 whisper would become a footnote. The team would move on, so they planned the observations. They picked the transits. They held their breath. They waited for Webb to slowly turn its golden mirror toward that one tiny point of light, and they prepared themselves for an answer that could go either way. And when the data finally came back, what they saw was not just a confirmation. It was something louder than they had imagined, loud enough to terrify them. The MIRI instrument inside Webb is one of the strangest pieces of technology ever flown into space. It is wrapped in shields. It is cooled to a temperature colder than almost anything in the natural universe. Without that deep cold, MIRI could not do its job. It would drown in its own heat. That cooling matters because mid-infrared light is, in plain terms, heat. Anything warm glows in this range. Stars glow. Planets glow. Even the camera itself glows, if you let it. To photograph faint heat from a planet trillions of miles away, you have to silence every nearby source of warmth, including the camera's own body. So MIRI sits inside Webb, frozen down to about -448 degrees Fahrenheit, colder than Pluto, colder than the darkest spots between stars. When the team aimed Webb at K2-18b for the new observations, MIRI's job was to catch a thin sliver of heat from a planet thousands of times fainter than its star. The planet had to pass directly between Webb and the red dwarf. During that brief window, the camera would record the starlight after it filtered through the planet's atmosphere. It took hours, then more hours, then many more. Multiple transits, slowly stitched together into a single, painfully detailed map of color. When the team unpacked the result, the fingerprint was right there. A clear dent in the spectrum at the wavelengths where dimethyl sulfide and a closely related cousin called dimethyl disulfide both absorb light. The shape was no longer a whisper. It was a clean, defined dip in the data, the kind of dip that does not appear by accident. The chemistry of the two molecules is similar. Both contain sulfur. Both come, on Earth, from living organisms. Both leave overlapping fingerprints in the mid-infrared. MIRI could not yet tell which of the two it was seeing, or whether both were present together. What it could say, with strong confidence, was that one or both were there. The team ran their statistics. The result was a 3 sigma signal. That is the famous 99.7% confidence level. In simple language, only 3 out of every 1,000 random datasets could fake this pattern by pure chance. For most fields of science, that is more than enough to publish a result with confidence. But astronomy has a stricter rule for claims this huge. To officially announce a discovery as real, scientists want 5 sigma. 5 sigma means a chance of less than 1 in a million that the result is random. K218b had crossed 3 sigma. It had not yet crossed 5 sigma, so the team could say something stunning, but not the final word. Madhusudan described what he felt in a careful sentence. He said this was the strongest evidence yet of life beyond Earth, and he meant every word of that. Strongest evidence, not proof, not confirmation, not the biggest discovery in human history, but the strongest evidence we had ever held. The signal was real, the math was solid, the fingerprint was clear, and yet a wall stood between this moment and the day humanity could finally say, out loud, that we are not alone. That wall is built out of pure statistics. And to understand why scientists treat it almost like a sacred line, you have to step inside the strange logic of how they decide what counts as truth. Numbers can lie when nobody explains them. 99.7% sounds like total certainty to most people. If a doctor told you a treatment had a 99.7% chance of working, you would probably trust it without question. So when the headlines reported that Webb had detected a biosignature at this confidence, many readers reasonably thought scientists had basically found alien life. The truth is stranger. In daily life, 99.7% is excellent. In science, especially in physics and astronomy, that same number sits in an awkward middle ground. Strong enough to pay attention, not strong enough to bet civilization on. To understand why, picture a simple example. Imagine flipping a coin 1,000 times. By chance alone, you might get a streak of heads that looks impossible. The longer you flip, the more weird streaks will show up. If you only count rare patterns, your data will eventually fool you. So scientists use a measure called sigma to estimate how likely a result is to be a real signal versus a freak streak in the noise. 1 sigma is weak, 2 sigma is interesting, 3 sigma is the level of the K218b result, where the chance of being random is about 3 in 1,000. 4 sigma starts to look serious. 5 sigma, the gold standard, means the chance of being random is less than 1 in 3.5 million. Why so strict? Because astronomers have been burned before. There is a long history of 3 sigma signals that turned out to be wrong. Faster than light particles, phantom planets, mystery signals from distant galaxies. Each time, scientists felt confident. Each time, after more data, the signal vanished. So the field learned, painfully, to demand more before declaring something real. There is another reason. The number of things you look at matters. Webb has stared at thousands of stars and planets. If you scan that many targets, you will eventually see a 3 sigma dip somewhere, just by luck. That is called the look elsewhere effect. The more places you search, the more likely random noise will mimic a real signal. For the K218b detection, the team did the math carefully. They were not looking randomly. They were testing a specific molecule in a specific atmosphere with a clear hypothesis from earlier data. That makes the 3 sigma result meaningful. It does not make it final. There is also the question of the molecule itself. Even at 3 sigma, MIRI cannot easily separate dimethyl sulfide from dimethyl disulfide, or from a few other, less famous molecules with similar fingerprints. Imagine recognizing a friend by the sound of their footsteps. You might be 99.7% sure it is them, but if their roommate has the same shoes, you cannot rule out the wrong person walking in. To go from this moment to a real discovery, scientists need 3 things. They need more data, ideally from new transits with longer exposure. They need to clearly separate dimethyl sulfide from its cousins. And they need to rule out, one by one, every non-living way the chemical could form in that strange hydrogen sky. Each of those steps is hard. Each is being attempted right now. Until they are done, the planet sits at the edge of the most important wall in modern astronomy, a wall scientists call 5 sigma. and crossing it has its own history of triumph, disaster, and surprise. 5 Sigma is the line. Cross it, and a result enters the textbooks. Fail to cross it, and your finding stays a candidate, sometimes forever. The number itself sounds small, a chance of less than 1 in 3.5 million that a result happened by accident. But the journey to reach that level can take years and demand huge amounts of telescope time, computing power, and human stubbornness. The 5 Sigma rule was born from heartbreak. In the middle of the last century, particle physicists kept announcing new particles based on data that looked solid. Many of those particles turned out to be ghosts. Statistical noise dressed up as discovery. After enough embarrassments, the community quietly agreed on a tougher line. Nothing would be called a real find without crossing 5 Sigma. That standard then spread to many fields, including the search for new planets, new black holes, and now possible alien life. Some of the most famous moments in modern science involve crossing this wall. The Higgs boson, the long-hunted particle that gives other particles mass, became a confirmed discovery only after physicists, in 2 separate experiments at the Large Hadron Collider, both crossed 5 Sigma in the summer of 2012. The first signs of the Higgs had appeared earlier as a 3 Sigma whisper, the same level that K218b sits at now. Scientists knew better than to celebrate. They waited. They collected more data. When the line was finally crossed, champagne came out. Gravitational waves, the tiny ripples in space caused by colliding black holes, also waited at the wall. The first real detection in 2015 swept past 5 Sigma in spectacular fashion. That clarity is why the discovery was trusted instantly and earned a Nobel Prize within 2 years. For K218b, the gap from 3 Sigma to 5 Sigma is not just a number. It is the gap between an exciting candidate and a confirmed truth. Closing that gap will require many more transits observed by Webb. Each transit lasts only a few hours. Webb can only observe each one when the planet aligns perfectly with its star and Earth. That alignment happens roughly once every 33 days. The data from each transit is then carefully cleaned, calibrated, and stacked together. The more transits, the stronger the signal becomes, assuming the signal is real. If the chemistry is truly there, more data will pull the signal up. The dent in the spectrum will deepen, the fingerprint will sharpen, the confidence will climb past 4 Sigma, then toward 5. If the signal is not real, the opposite will happen. Adding more data will smear the dent away. The fingerprint will fade. The number will fall back. That is the merciless beauty of statistics. It does not care who is right. It only cares about the truth. Some scientists worry that even reaching 5 Sigma will not settle the question. Because even if dimethyl sulfide is definitely there, that does not prove it came from life. The number tells you the molecule exists. It does not tell you what made it. This is the second wall, just as tall, just as stubborn. Detection is one battle, interpretation is the next, and on K218b, the interpretation battle has already begun. The first major idea on the table is one of the most beautiful theories in modern astronomy. It claims this distant planet might be hiding an ocean unlike anything we have ever seen. Around 5 years ago, Madhusudan and a small group of colleagues began asking a strange question. What if planets bigger than Earth, but smaller than Neptune, sometimes had oceans? Not the tiny puddles we sometimes find frozen on small moons, but real oceans, hundreds of miles deep, stretching across an entire world. The idea sounded almost like fantasy at first. Most scientists treated sub-Neptunes as small, hostile gas worlds, crushed by their own weight, wrapped in deep, hot hydrogen layers. No surface, no water you could swim in, just gas getting denser the deeper you went, until pressure made it act like a liquid. But Madhusudan ran the numbers. Under the right conditions, he found, the hydrogen layer might be much thinner than expected. If that thin sky sat on top of a deep, cool ocean, the planet would not just be habitable, It might be a paradise for tiny life forms swimming in the dark. He gave these worlds a new name, Hycean planets. The word comes from hydrogen and ocean. The concept describes a sub-Neptune wrapped in a slim atmosphere of hydrogen gas, sitting above a vast water ocean stretching all the way around the world. The Hycean idea immediately attracted attention. It expanded the kind of places where life might exist. It also matched several puzzles from real web data. Sub-Neptunes are extremely common in our galaxy. If even a fraction of them are Hycean worlds, the number of potentially habitable planets in the universe explodes upward by factors no one had calculated before. Suddenly, the sky is full of alien oceans. K2-18b became the test case. Its size matched the Hycean range. Its atmosphere held hydrogen, methane, and carbon dioxide, all matching Hycean predictions. Its temperature, given its distance from its star, would allow liquid water at the surface, assuming the right cloud cover. The 2023 detection of methane and carbon dioxide together fit the Hycean model better than the older mini-Neptune model. And now a possible biosignature seemed to land on top. Picture standing on the surface of such a world. There would be no surface at all, in the normal sense. The bottom of the hydrogen sky and the top of the global ocean would meet without a beach, without a coastline, without islands. As far as anyone knows, just an endless, dim expanse of deep water rolling under a colored haze. The light from the red dwarf would filter through clouds in muted tones, maybe rusty orange, maybe pale red, maybe a deep, eerie pink. Storms would brew at scales nobody on Earth has ever seen. The hydrogen winds, blowing across thousands of miles of open water, could whip up waves taller than mountains. There would be no land for the waves to crash into, so they might roll for weeks before fading. Below the surface, the water would grow stranger fast. Pressure would mount with depth. Temperatures could shift in odd ways. Very deep down, exotic forms of ice that only exist under extreme pressure might form, even if the water above stayed warm and liquid. In all that strangeness, microbes might live. They might float in the upper layers, soaking up the dim red light. They might cluster around heat sources rising from below, and as part of their life cycles, they might release dimethyl sulfide into the air above them, just as Earth's plankton do. That is the dream. The reality, as always, is more complicated, because not every scientist agrees that Hycean worlds even exist, and the debate over what kind of place K2-18b really is could decide whether this story ends in triumph or quiet disappointment. If K2-18b really is a Hycean world, the ocean covering it would not behave anything like Earth sees. It would be deeper, heavier, and pushed around by forces our planet has never seen. Start with depth. On Earth, the average ocean is about 2.5 miles deep. The deepest point, the Mariana Trench, sinks just under 7 miles. On a Hycean planet, the math could be brutal. Depending on how much water sits above the rocky core, the ocean on K2-18b could be hundreds of miles deep, possibly more than 1,000. There may be no real bottom in any sense a swimmer would recognize, just water, getting darker, hotter, and more compressed forever. Now add the hydrogen sky. Hydrogen is the lightest gas in the universe. A thick layer of it pressing down on a global ocean creates strange effects. The atmosphere can be denser at the surface than Earth's atmosphere is in our deepest valleys. Sound would travel differently. Light would scatter in odd patterns. Storms would behave like nothing in our weather books. Wind plays a key role here. On Earth, wind builds waves by pushing on the surface. The longer the stretch of open water, called the fetch, the bigger the waves grow. A hurricane on the open Atlantic can build waves over 100 feet tall because it has thousands of miles of water to push against. On a global ocean, the fetch never ends. A storm on K2-18b could blow across an unbroken sea for weeks or even months. There are no continents to break the wave's growth. There are no shallows to drain its energy. Combined with strong gravity that pulls back hard once a wave starts to rise, the result could be ridges of water taller than any mountain on Earth. Some researchers have run simulations of these endless oceans. The results show waves that build slowly, traveling enormous distances at speeds far higher than anything on Earth. They could roll for thousands of miles before crashing into other waves and creating chaotic mountainous swells. If you could fly above the surface, you might see endless rolling ridges of dark water glowing faintly under the red sun. Below the surface, currents would be just as strange. Heat from inside the planet, plus radiation pouring in from above, could drive massive convection cells. Layers of warm and cold water would shift in patterns we have no maps for. The mixing might spread nutrients across the entire ocean in ways Earth's seas never manage. For potential life, all of this matters. Wild oceans are rich oceans. Strong mixing brings minerals and gases up from the deep, feeding any organisms living near the surface. Steady, dim light from the red sun would fall on the upper few hundred feet of water. Below that, total darkness, where life would have to feed on heat or chemistry instead of sunlight. There is one more eerie possibility. The crushing pressure deep below could turn ordinary water into exotic forms of ice that only exist under extreme conditions. These strange ices behave like rock. They could form a slow, grinding floor under the warm liquid above. Above that floor, regular water. Below it, more water in stranger forms still. A planet built in layers, like an onion of liquids and ices. If even microbes float in the upper layers of this monster ocean, they would shape its chemistry. They could pump dimethyl sulfide into the hydrogen sky in unimaginable amounts, numbers that match what Webb thinks it just saw. But before any life could survive there, the planet first has to be the right temperature. And on that question, the data is starting to fight itself. K2-18b sits in the habitable zone of its star. That phrase makes the planet sound cozy, like a house at just the right distance from a warm fire. The reality is far less reassuring. Habitable zone is a rough idea. It only means the planet receives enough starlight to keep liquid water at the surface. If everything else cooperates. Atmosphere matters. Cloud cover matters. The kind of star matters. The actual temperature on the surface can be wildly different from what the simple math predicts. For K2-18b, the simple math says the upper atmosphere is around -8 degrees Fahrenheit, cold by Earth standards, but not impossible. With a thick blanket of hydrogen wrapping the world, the surface beneath could be much warmer. Some early estimates put it close to room temperature. Others put it boiling hot. Others put it frozen solid. The truth depends on details we cannot yet measure. The biggest unknown is the cloud layer. Clouds reflect light. On a planet with the right kind of clouds, a huge amount of starlight bounces back into space before reaching the surface. That cooling effect can be the difference between a habitable ocean and a steam bath. On K2-18b, scientists believe clouds or hazes do exist in the upper atmosphere. Webb's earlier data hinted at them, but how reflective they are and how thick they reach is still unknown. If the clouds are bright and thick, the surface stays cool. Liquid water holds. A Haitian ocean is possible. Microbes can live. Dimethyl sulfide can rise into the air, exactly as Webb seems to be detecting. If the clouds are thin, the surface gets hammered with starlight. The temperature climbs. Water turns to vapor. The ocean becomes a steaming sky. The whole Haitian theory collapses, and the dimethyl sulfide signal would have to come from some other process. A different group of scientists has run their own models of K2-18b and reached opposite conclusions. They argue the planet might not be a Haitian world at all. They suggest it could be a regular sub-Neptune, with no real ocean and no surface in the human sense. In that version of the story, the methane and carbon dioxide come from chemistry happening deep in the hydrogen layers. far below where any life could survive. There would be no place for tiny creatures to swim. There would be no source for dimethyl sulfide except some strange, unknown chemistry. A third group has gone even further. They argue that the temperature inside the lower atmosphere could be extreme enough to make the supposed ocean a layer of supercritical water. That is, water under such heat and pressure that it does not act like a liquid or a gas. It becomes something in between, a weird, dense fluid that no Earth life could survive in. So which version is right? Right now, nobody knows. Webb cannot peer through the cloud layer to see the actual surface. No future telescope on the books will be able to either, at least not for many years. The temperature debate may not be settled until the next generation of giant ground-based telescopes comes online. This is what makes the dimethyl sulfide signals so confusing. The molecule may be real, the atmosphere may be a Hycean sky, or the molecule may be real, but the sky may be a chemical furnace where life cannot exist. Each answer rewrites the meaning of the discovery. Even so, one strange fact keeps drawing scientists back. The planet is bigger than Earth, yet the math suggests it might still hold liquid water, and the reason for that hides in the same equations that built Earth itself. It sounds wrong at first. K2-18b is more than 2 times the width of Earth and several times its mass. Surely a planet that big would crush its own oceans, or never have them in the first place. The story turns out to be more interesting than that. Size, on its own, does not destroy water. What matters is the balance between gravity, temperature, atmosphere, and how the planet was built in the first place. Each of those pieces points, in K2-18b's case, toward a possible water world. Start with how planets form. Around a young star, gas and dust swirl in a flat disk. Bits clump together. Some clumps grow fast. The fastest grow large enough to pull in huge amounts of hydrogen and helium gas, becoming gas giants. The slowest end up as small, rocky worlds. In between sit the sub-Neptunes, like K2-18b. They grow big enough to hold light gases, but not big enough to swallow most of what is around them. What makes K2-18b interesting is where it likely formed. Astronomers believe the planet was built farther out, in colder regions of its solar system, where ice was easy to gather. Then it slowly moved inward toward its star. When it arrived in its current orbit, it brought a huge amount of water with it, frozen at first, then melted by the warmer light of its red dwarf. The water did not boil away because the planet's gravity is strong enough to hold onto it. It also did not all freeze, because the planet is close enough to its star to keep the surface above 0 degrees Fahrenheit, especially under a blanket of hydrogen. That blanket is the key. Hydrogen is light, but it is excellent at trapping heat. Even a thin hydrogen layer can act like an enormous greenhouse, holding warmth on the surface below. Over hundreds of millions of years, that warmth could keep a global ocean liquid even as the upper atmosphere stays cold. Imagine standing at the bottom of a deep building during winter. The roof is freezing, but the ground floor stays warm because the structure traps heat from below. Now scale that up to a planet. The top of K2-18b's atmosphere may be cold enough for ice to form in the high clouds. Hundreds of miles below, near the supposed ocean's surface, the temperature could sit somewhere life would recognize. Gravity on K2-18b would be strong, possibly 2 to 3 times Earth's. That extra pull squeezes the air closer to the surface, increasing pressure and helping water stay liquid even at higher temperatures. It also keeps the entire ocean held tightly against the planet, instead of letting it puff out like a thin shell. There is another reason this matters. On a world with strong gravity, a deeper atmosphere protects the ocean below. Cosmic rays, ultraviolet light from the red dwarf, and high-energy flares all get absorbed or scattered before reaching the surface. Anything alive in the water would live under a natural shield made of gas and depth. Put it all together, and K2-18b looks less like a giant gas balloon and more like a very strange version of Earth. A water world that grew up in a different neighborhood, kept its inheritance of ice, and cooked it gently into a planet-wide sea. If that picture is correct, then the next number is what changes everything. The amount of dimethyl sulfide Webb saw in the air is not small. It is far beyond anything Earth produces, and that single fact has shaken the entire field. When Webb's MIRI camera caught the dimethyl sulfide fingerprint in K2-18b's atmosphere, the team did not just confirm the molecule, they estimated how much of it was there. The number that came out of the math made even seasoned scientists pause. On Earth, dimethyl sulfide is a trace gas. It fills the air above the oceans, but in tiny concentrations. We measure it in parts per billion, and even those numbers are small. It rises off the surface, mixes into clouds, and gets broken down by sunlight within a few days. Despite that fast destruction, our oceans replace it constantly. The total amount in the air at any moment is still far less than the carbon dioxide or methane around us. On K2-18b, the estimated levels reach something like 10 parts per million, at least. That number is at least 1,000 times higher than anything Earth's biosphere produces, possibly far more. To understand what that means, picture two oceans side by side. One is Earth, gently humming with phytoplankton, pumping out its small breath of dimethyl sulfide. The other is K2-18b, releasing the same molecule at a rate so much higher that it floods the entire atmosphere. If life is making it, that life is doing so with frightening intensity, there are two ways to read this. The first reading is biological. If life on K2-18b is the source, then the planet is teeming. Not a few microbes scattered here and there, but enormous populations spread across an ocean the size of a world. Every cubic mile of water near the surface might be alive with microscopic organisms working in unison. Their breath would saturate the sky. That image is almost too much to believe. It would make K2-18b not just an inhabited planet, but a wildly inhabited planet. Earth's oceans, by comparison, would look almost empty. The sheer richness of biology required to produce that signal would force scientists to rewrite assumptions about how easily life can fill a world once it gets started. The second reading is more cautious. Maybe the molecule's lifetime in K2-18b's atmosphere is much longer than on Earth. On our planet, sunlight breaks down dimethyl sulfide quickly, so the gas never builds up. In a hydrogen-rich sky around a dim red star, the chemistry could be very different. The molecule might survive for years instead of days. If it stays around longer, even a small biosphere could let it accumulate to high levels over time. That second reading still allows life as the source, but a much more modest amount. A planet covered in microbes, but at densities closer to Earth's. Their slow output would gather instead of vanish until the air filled with the gas. Either reading still points to biology as the most natural explanation. Both readings unsettle scientists, because both imply that life on K2-18b is not borderline, it is real. Either it is everywhere, or it has been busy for a very long time. That is exactly why the result has caused such intense debate. The amount is too high to ignore, and too high to easily reproduce in lab experiments without invoking life. Researchers have already begun running new chemistry simulations, asking whether any non-biological process could create dimethyl sulfide at these levels in a hydrogen sky. So far, no one has produced a clean answer. Pressing these clues together, the air of K2-18b looks less like ours every time someone studies it, and the differences between its sky and our own sky are more important than any number could express. Stand outside on a clear day and breathe in. The air around you is mostly nitrogen, with a strong dose of oxygen, a tiny bit of argon, and trace amounts of carbon dioxide, water vapor, and other gases. Your lungs evolved over hundreds of millions of years to use exactly this mixture. Change it even a little, and you would be in trouble. Now imagine standing on the deck of an impossible ship floating somewhere on K2-18b's hydrogen sky. The chemistry around you would be unrecognizable. Hydrogen would dominate. Pure hydrogen, the lightest gas in the universe, would make up the majority of the atmosphere. Helium would mix in, just like in the gas giants of our solar system. Together, those two gases would form the bulk of the air. You could not breathe it. There is no oxygen for your lungs to grab. You would suffocate quickly, even though the sky around you is full of molecules. Inside that hydrogen and helium mix, smaller amounts of other chemicals would float. Webb has now seen at least 4: methane, carbon dioxide, water vapor, and, most strikingly, possible dimethyl sulfide. Each of these is in trace amounts compared to the hydrogen, but each is rich enough to leave a clear fingerprint on starlight passing through the sky. This recipe is unlike anything in our solar system. Mars has a thin carbon dioxide atmosphere with a faint trace of methane that scientists have argued about for decades. Venus has a heavy carbon dioxide atmosphere with sulfuric acid clouds, no liquid water, and pressures that crush metal. Jupiter and Saturn have hydrogen and helium skies, but no signs of biological molecules, and no surface where life as we know it could exist. Earth, with its nitrogen and oxygen mix, methane, and water cycle, stands alone. K2-18b sits somewhere none of those examples cover. The presence of methane and carbon dioxide together in a hydrogen atmosphere is itself unusual. On a normal sub-Neptune, those two gases tend to react and break each other down over long timescales. To find both at once, in clear amounts, suggests something is constantly making one or the other. On Earth, methane is replenished mainly by life. Carbon dioxide is replenished by volcanoes, oceans, and life again. On K2-18b, the source is unknown. Some scientists argue it could be a hidden ocean with chemistry similar to Earth's. Others argue it could be deep atmospheric processes, far below any habitable layer. Add dimethyl sulfide to that mix, and the comparison gets stranger. In Earth's atmosphere, dimethyl sulfide is a delicate, short-lived molecule. Sunlight tears it apart within days. Yet our oceans replace it so fast that there is always some present. On K2-18b, the cooler red light, the hydrogen-rich chemistry, and the lack of strong ultraviolet may slow that breakdown drastically. The molecule could linger for years instead of days. That alone could explain the high concentration without requiring a biosphere larger than Earth's. Slowed chemistry is a possibility, not a fact. Scientists are now running computer simulations of hydrogen atmospheres around red dwarf stars to test what happens to dimethyl sulfide under those conditions. The early results suggest the gas might indeed last longer, but not so long that it could build up by itself with no source. Something has to keep making it. If the source is biology, K2-18b becomes the most important planet ever discovered. If the source is some unknown chemistry, it may be the most important chemistry experiment ever observed in nature. Either way, the next missing piece in this puzzle is what should be there alongside the dimethyl sulfide. And the strange thing is, at least one expected molecule does not seem to be there at all. When Webb spotted dimethyl sulfide in K2-18b's air, scientists immediately looked for its companions. On Earth, biology rarely produces a single chemical alone. Living systems leak whole families of related molecules because real chemistry tends to come with side effects. Where dimethyl sulfide rises, other gases follow. One of those expected companions is called ethane. Ethane is a small molecule made of 2 carbon atoms and 6 hydrogen atoms. On Earth, it appears in very low amounts in the air, and a tiny but steady portion of it forms when sunlight breaks down dimethyl sulfide. Wherever you find significant levels of dimethyl sulfide, you should also find a faint trail of ethane drifting nearby. It is a kind of chemical shadow. On K2-18b, that shadow is missing. Scientists have searched the spectral data for Ethane's fingerprint. So far, no signal has shown up. The amount, if any, is so small that Webb cannot see it. That absence has unsettled some of the same researchers who found the dimethyl sulfide signal exciting. A University of California astronomer named Eddie Schwieterman put it bluntly. He said the absence of ethane makes him feel something has been missed. There are several possible reasons. The first possibility is that the chemistry on K218b really is different. In a hydrogen atmosphere around a red dwarf, the ultraviolet radiation that breaks dimethyl sulfide into ethane on Earth may be far weaker. Without that radiation, the breakdown reaction could happen slowly or barely at all. In that version of the story, dimethyl sulfide builds up while ethane remains almost absent. That fits the data, but it requires the breakdown chemistry to be much slower than anyone has measured in a real lab. The second possibility is more troubling. Maybe the dimethyl sulfide signal is partly wrong. The fingerprint Webb saw could be a different molecule or a mix of molecules that happens to look a lot like dimethyl sulfide. Computer models of mid-infrared spectra are not perfect. Several less famous chemicals have overlapping shapes. If one of those chemicals is contributing to the signal, the team's interpretation would have to shift, and the link to life would weaken. The third possibility is the most uncomfortable. Maybe the signal is real, but it is being faked by the instrument itself. MIRI is an extremely sensitive camera. Tiny shifts in temperature, vibration, or calibration can leave faint patterns in the data that look like real chemistry. Several independent teams have reanalyzed the same Webb data and reached different conclusions. Some find the dimethyl sulfide signal robust. Others find it fragile, depending heavily on choices made while cleaning the data. This is where science becomes a contest of careful work, not louder claims. 2 papers published within months of the original announcement argued that the dimethyl sulfide detection might dissolve under different processing methods. One reached a conclusion that K218b does not yet meet the standards of evidence for life. That does not mean the original team is wrong. It means the case is not closed. The missing ethane is one of several reasons for caution. Another is the strange absence of related sulfur compounds that should appear if a true biological soup were rising into the sky. The team behind the original detection has acknowledged these gaps. They have called for more observations, more lab experiments, and more independent reviews. They are not running from the doubts. They are walking straight toward them. But before the doubts can be answered, scientists have to ask whether dimethyl sulfide could possibly be made by something other than life. And the search for non-living explanations has turned out to be a deeper rabbit hole than anyone expected. The dream of finding life on another world depends on one stubborn rule. The chemicals you detect must have no reasonable non-living source. If something else can make the molecule, biology becomes only one possibility among many. For dimethyl sulfide on K218b, the search for non-biological sources has become a race against the clock. On Earth, the rule is clean. We have studied this gas for over a century. We know how it forms, where it forms, and what makes it. Living organisms are the only meaningful source. Lab experiments have tried for decades to make significant amounts of it without biology, and they have failed. But Earth chemistry is not universal chemistry. Our atmosphere is rich in nitrogen and oxygen. Our temperature is mild. Our sunlight is yellow and bright. Our pressure is moderate. Each of those features shapes which reactions can happen here. Move to a different world with a different atmosphere and a different star, and the rules shift in ways that are hard to predict. K218b breaks every Earth rule at once. The atmosphere is mostly hydrogen, the most chemically active simple gas in the universe. The light from the red dwarf is dimmer and redder than our sun, with a different mix of ultraviolet radiation. The pressure is higher. The temperatures, especially deep down, are much warmer than the upper atmosphere readings suggest. Each of these conditions can drive reactions that simply do not happen on Earth. In a lab on Earth, mixing certain sulfur-rich compounds with hot hydrogen and ultraviolet light has been shown to produce small amounts of dimethyl sulfide, not biological, just chemistry. The amounts are tiny, far below the levels Webb saw in K2-18b's air. But the experiments have only been running for a few years, and they cannot exactly copy a planet's full chemistry. Some researchers have proposed that, given enough time and the right conditions, K2-18b's hydrogen atmosphere might cook up the molecule slowly. Years would pass between batches. The amount made each year would be small, but because the molecule could last much longer in a hydrogen sky than on Earth, even a slow process could let the gas accumulate to high levels over very long stretches of time. The math gets tense here. The known non-biological reactions are too slow to easily fill the planet's air with dimethyl sulfide at the levels detected. Yet they cannot be ruled out completely. The hydrogen atmosphere on K2-18b is unlike anything humans have ever observed up close, so any prediction we make is partly a guess. There is also the question of unknown reactions. New chemistry is discovered all the time. A reaction nobody has thought of, in conditions nobody has tested, could quietly be at work on K2-18b. That possibility is impossible to disprove from a distance. The only way to settle it is to do more lab work and more modeling here on Earth, while observing the planet more carefully with telescopes. So the team has stepped back from any direct claim of life. They have said the signal is there. They have said biology is the most likely known source. They have not said it is the only source. That careful posture has not stopped some of the most creative theories from emerging. One of the most popular involves a place we usually associate with destruction, not creation: volcanoes, the fiery vents that shape rocky planets. The question is whether they could deliver dimethyl sulfide on a world like K2-18b. The answer turns out to be more complicated than anyone first thought. Volcanoes are nature's chemists. They take molten rock from deep inside a planet, push it to the surface, and release a flood of gases into the atmosphere. On Earth, volcanic gas is a stew of water vapor, carbon dioxide, sulfur dioxide, hydrogen sulfide, and a handful of trace compounds. Could one of those volcanic gases actually be dimethyl sulfide or break down into it? This question has been quietly chewed over by scientists ever since the original detection. The answer, as it stands today, is mostly no. Volcanic eruptions on Earth do release sulfur in large amounts. The famous yellow stain around active vents comes from sulfur compounds. Many of those compounds smell sharply, and people often confuse the smell with the scent of the ocean. But the chemistry is different. Volcanic sulfur tends to come out as sulfur dioxide and hydrogen sulfide, not dimethyl sulfide. To turn one into the other, you need carbon, hydrogen, and very specific conditions. Volcanoes alone do not handle that handoff well. Still, K2-18b is not Earth. Could its volcanoes, if it has any, be different? This is where the picture gets harder. We do not even know if K2-18b has volcanoes. The planet may not have a solid surface at all. If it really is a Hycean world, its outer layer is liquid water resting on a rocky core hundreds of miles below. Volcanic activity, if it exists, would happen at the bottom of that ocean, with vents pumping gases up through huge depths of water. That kind of underwater volcanic chemistry is fascinating. On Earth, hydrothermal vents at the bottom of the ocean form rich chemical environments where strange microbes thrive. They release sulfur compounds, build mineral towers, and feed entire ecosystems with no sunlight. Even so, dimethyl sulfide is not a major output of these vents. Other sulfur molecules dominate. If K2-18b's vents work in similar ways, they would seed the deep ocean with sulfur, but they would not directly fill the upper atmosphere with dimethyl sulfide. The molecule would need to be assembled later, somewhere in the water column, by something else. On Earth, that something else is biology. On K2-18b, that role is the missing piece. Some researchers have asked whether the rocky core itself could give off dimethyl sulfide directly during certain rare reactions. The math does not favor it. The amounts would be tiny. They would also be unlikely to make it through a hundreds of miles deep ocean and then a thick hydrogen atmosphere without breaking down on the way. There is one more reason the volcanic theory looks weak. K2-18b's atmosphere is in chemical balance in ways that suggest a steady, ongoing source for the gas. Volcanoes are sporadic. They erupt, settle, and erupt again. They do not produce a smooth, continuous stream of any single molecule. To match Webb's data, the source would have to be steady. Biology fits that pattern. Volcanic activity does not. For now, most scientists treat the volcanic option as unlikely, but not impossible. Like every part of this story, it cannot be killed off completely without more data. And K2-18b is too far away to send any kind of probe in our lifetimes. We have to settle for clever science from 124 light-years out. That leaves one more strange option to consider, an idea that does not involve life, planets, or volcanoes at all. It involves visitors from far outside the solar system, tiny chunks of ice and dust that travel on lonely orbits across the galaxy. Comets. In recent years, astronomers have made a strange discovery about comets. Some of these icy travelers carry surprising chemicals inside their frozen bodies. When a comet passes close to a star, its surface heats up, and gases stream off into space. By scanning that gas, scientists can read what the comet is carrying. In 2023, a careful look at a passing comet inside our own solar system found something unexpected: dimethyl sulfide, the same molecule Webb later spotted at K2-18b. It was a small amount, but it was there. That detection cracked open a new possibility. If comets can carry dimethyl sulfide naturally, without biology, then planets bombarded by comets over millions of years might end up with measurable amounts of the gas in their atmospheres. The chemical would not be made by life. It would be delivered, like a slow chemical mail service, by ice balls flung in from the outer reaches of the solar system. This idea immediately changed how scientists thought about K2-18b. Could it be that comets bombarding the planet seeded its atmosphere with dimethyl sulfide over time, with no living thing involved? The math, again, is not friendly to this theory. The amount of dimethyl sulfide detected on K2-18b is enormous, thousands of times higher than what Earth produces. To match those levels by comet delivery alone, the planet would need to be hit by comets constantly, in numbers that would also rip apart the planet's atmosphere and reshape its surface. The bombardment would leave clear marks. So far, those marks are not there. There is also the timing problem. Comets in our solar system carry tiny amounts of dimethyl sulfide. Even in a system with many more comets than ours, the supply rate would be slow. The molecule, even if its lifetime is longer in a hydrogen atmosphere, would still break down over millions of years. To keep the air saturated to the levels Webb measured, deliveries would have to be constant and overwhelming. That said, comets cannot be entirely dismissed. They show that dimethyl sulfide can form by non-biological means in some conditions. They prove the molecule can exist outside the activity of phytoplankton and other Earth organisms. That single fact is enough to weaken the simple claim that dimethyl sulfide always equals life. Most likely, comets contribute small amounts to many planetary atmospheres, including K2-18b's. They explain a portion of the signal. They do not explain all of it. The original team has accepted this carefully. They have said comet contamination is possible. They have said it cannot account for the full level of dimethyl sulfide they see. Their best estimate still points to a continuous, planet-wide source. On a world with possibly habitable conditions, the simplest match for that kind of source is biology. A simple match is not a proven case. Every piece of data still has to be tested again. The team behind this whole story has spent years getting to this moment. Their journey involves more than telescopes. It involves human stubbornness, late nights, and a quiet kind of bravery because they knew the world would tear apart any claim they made. That story, the human story behind the science, is just as gripping as the planet itself. Long before Webb pointed at K2-18b, before the headlines, before the social media debates, there was a small group of researchers asking quiet questions about strange planets. The leader was Niku Madhusudhan, a soft-spoken professor at the University of Cambridge who had spent his entire career chasing alien atmospheres. He grew up in India, drawn to physics from an early age. He earned his PhD at the Massachusetts Institute of Technology, focused on a topic that few scientists in the early years of exoplanet research took seriously: reading the air of planets around other stars. At the time, the idea sounded almost like magic. The signals were too faint, the instruments were too weak, the math was a nightmare, but he kept working. By the early years of last decade, technology was catching up. The Hubble Space Telescope began offering tantalizing glimpses of alien atmospheres. Madhusudhan and his collaborators turned those glimpses into careful science. They learned how to extract real chemistry from terrible data. They learned how to test their tools against known planets. They became experts at reading the unreadable. When the Webb telescope launched, his team was ready. They had spent years building the methods needed to handle the new data. They had also picked their early targets carefully. K2-18b was at the top of the list. That choice was not luck. It was years of preparation. K2-18b had been discovered in 2015 by NASA's Kepler Space Telescope. Hubble had hinted at water in its atmosphere in 2019, though that signal turned out to be tricky to confirm. Madhusudhan and his team kept the planet in their sights. When Webb came online in late 2021, they applied for telescope time on it almost immediately. The first results, in 2023, were everything they hoped for: methane, carbon dioxide. The strong fit with the Haitian theory the team had been quietly developing for years. A weak hint of dimethyl sulfide. They published carefully. They accepted criticism gracefully. They went back for more data. 2 more years of work followed. New observations, new analyses, new checks. Every step had to survive intense review. Madhusudhan often spoke about the importance of caution. He described the team's mood as a mix of excitement and discipline. He said it would be wrong to claim life. He said the data did not yet allow that. He said only that this was the strongest case anyone had ever built for biology beyond Earth. His co-authors echoed him. One of them, a researcher named Mons Holmberg, told the Washington Post that the team was looking at one of 2 huge possibilities. Either a new chemical process was at work, or they were seeing the first signs of biology beyond Earth. Both options would change science. The team has chosen to continue gathering evidence carefully rather than rushing to dramatic claims. They have planned new observations. They have invited rival teams to test their data. They have run side-by-side comparisons with other interpretations. They are doing exactly what good scientists are supposed to do, and they are doing it under intense public attention. That kind of bravery is unusual in a field where most claims are quietly tested in private. Madhusudhan and his team chose to share their findings while still holding their own conclusions back. The result is a real-time experiment in how humanity handles a moment that may or may not become history. That experiment took an unexpected turn when another group of scientists looked at the same data and reached a very different result. Within months of the original announcement, a competing group of researchers released their own analysis of the same Webb data. They reached a conclusion that shook the entire conversation. The dimethyl sulfide signal, they argued, might not even be there. This was not a casual challenge. The new study came from a respected team that included scientists at NASA. They downloaded the same web files used by the Madhusudhan group, ran their own data cleaning routines, and looked for the same fingerprints. What they found was very different. In their analysis, the strong signal at 3 sigma either weakened or disappeared depending on how the data was processed. They argued that the result was extremely sensitive to small choices made during cleaning. Specifically, they pointed at a method called wavelength binning, which controls how the spectrum is sliced into pieces before being checked for chemical fingerprints. Different choices led to different answers. In their preferred method, the dimethyl sulfide signal collapsed. In the original team's method, it remained. The rival study stated that nearly 9 out of 10 of their tested processing methods gave no clear evidence for dimethyl sulfide. Only a narrow range of choices produced the strong signal the original team reported. That kind of disagreement is normal in early-stage science. Two careful teams can stare at the same data and reach different conclusions because the methods used to clean instrument noise are themselves an active research area. Webb's MIRI camera is brand new. The people studying it are still learning what kinds of small errors it produces. Until those errors are understood completely, every result that depends on them is fragile. The original team did not back down. They acknowledged the challenge, defended their methods, and pointed out that their approach was based on careful comparison with known calibration tests. They argued that the rival team's binning method may not be the best one for this kind of planet. They invited continued debate and further observation. A second set of independent researchers added another layer. Their work studied the entire range of Webb data on K2-18b, from the near-infrared to the mid-infrared. They concluded that some of the original chemistry, like methane and carbon dioxide, is robust. Other parts, like dimethyl sulfide, are more uncertain. They did not declare the signal fake. They said the case for it is weaker than the original announcement implied. This kind of crossfire is not a sign that science is broken. It is a sign that science is working. Strong claims must survive. Strong tests. K2-18b is now one of the most carefully scrutinized planets in the sky. Every shred of its data is being torn apart by competing teams using competing methods. Out of that battle, a clearer picture is slowly emerging. The atmosphere of K2-18b is real. Methane is real. Carbon dioxide is real. Water vapor is real. Dimethyl sulfide is uncertain. It might be there, it might not. The next round of Webb observations, already approved, may settle the question. For the public, the takeaway is simpler. The signal is not yet a confirmed alien biosignature. It is a candidate worth chasing with the most powerful instruments humans have ever built. A candidate that might either reveal life beyond Earth or expose a strange new chemistry happening 124 light-years away. Either outcome would be huge. And that is exactly why the next round of debate has focused on something even smaller than the molecule itself. It has focused on the noise inside the camera. The MIRI camera on Webb is one of the finest tools ever built. It can detect heat coming from objects so faint that earlier telescopes could not even tell they were there. But every instrument has flaws. Every camera adds its own pattern to the data it collects. Removing those patterns is one of the hardest jobs in modern astronomy. Imagine taking a photo of a friend at dusk with a long exposure. Your phone holds the shutter open for several seconds to gather light. The result usually has a soft glow, faint streaks where your hand moved, and tiny pinpoints of color noise scattered across the image. None of those features were really there. The camera made them. To recover the real picture of your friend, you would have to subtract all those artifacts. Webb does the same thing on a far larger scale. When MIRI records data from K2-18b, the raw output is full of artifacts. Tiny shifts in temperature, small movements of the telescope, calibration drifts inside the electronics. Each of those leaves a fingerprint in the data. If those fingerprints are not removed cleanly, they can mimic chemistry that is not actually present in the planet's air. This is the heart of the disagreement between the two teams analyzing K2-18b. They both saw artifacts in the raw data. They both removed them. They removed them differently. One way to remove instrument noise is to chop the spectrum into very narrow slices and average each slice. Another way is to use wider slices. A third way is to weight different slices differently based on how reliable each is. These choices may sound technical, but they have huge effects on the final answer. When the signal you are searching for is small, even tiny choices in cleaning methods can decide whether the signal stands or falls. For dimethyl sulfide on K2-18b, the molecule's fingerprint sits in a region of the spectrum that overlaps with several known instrument noise patterns. That makes the work especially treacherous. Each cleaning choice has the potential to either reveal a real chemical signal, or to scrub it away, or to invent a signal that was never there. This is why scientists are calling for many independent teams to study the same data using different cleaning methods. Only when the answer agrees across multiple approaches will the result be considered solid. Until then, the dimethyl sulfide signal lives in a narrow band of certainty depending on the methods used to clean the data. The good news is that astronomers know how to handle this kind of problem. They have decades of experience with similar situations. Each new instrument goes through a long phase of learning, where the community slowly builds a shared understanding of what the camera does. MIRI is still in that learning phase. Within the next 2 or 3 years, scientists expect to know its quirks much better. By then, the K2-18b data will likely be reanalyzed with better tools, and the dimethyl sulfide question may finally have a clean answer. For now, the data sits at the edge of certainty. The signal is real enough to argue about. It is not strong enough to settle. And while the technical debate continues, another debate has been raging on a different front. A debate not about whether the signal is real, but about how to interpret what it might mean. That argument turns on basic ideas about how to read scientific data, and in many ways, it has been more heated than the chemistry itself. In every field of science, there comes a moment when a discovery splits into 2 questions. Did we measure something? And does our measurement actually mean what we think it means? With K2-18b, both questions are alive at the same time, and both are fueling fierce debate. The first question is technical. Did Webb actually see dimethyl sulfide? As we have already explored, that question depends on data cleaning, instrument noise, and statistical thresholds. Different teams give different answers. The next round of observations is expected to help settle it. The second question is deeper. If the molecule really is there, what does it mean? Even within the team that announced the original detection, the language has been carefully chosen. They have not said this is alien life. They have said this is the strongest evidence yet of biological activity outside our solar system. Those 2 statements are not the same. Outside the team, the differences sharpen. Some scientists argue that no single chemical can prove life. They point to a long history of false starts. In the past, methane on Mars, sulfur on Venus, and strange seasonal changes on other worlds have all been proposed as biosignatures. None turned into confirmed life. Each had a non-biological explanation that eventually emerged. They warn that getting too excited about a single molecule, even one as suggestive as dimethyl sulfide, repeats those mistakes. Other researchers argue the opposite. They say dimethyl sulfide is special. Unlike methane, which can come from many non-biological sources, dimethyl sulfide is a much narrower fingerprint. Its lifetime, its chemistry, and its formation pathways all point strongly toward biology under the conditions we know. They believe that if the signal holds up, it is one of the cleanest biosignature claims ever made. This is not a clean split between believers and skeptics. Most scientists fall somewhere in the middle. They say, the signal is interesting, the case is strong, the evidence is not yet conclusive, and the next steps will involve much more data and many more teams. That cautious middle ground is exactly where good science usually lives. The public conversation, on the other hand, has often pulled in extremes. Some headlines treated the result as nearly proof of alien life. Others treated it as a near fraud waiting to be exposed. The truth, again, sits in the middle. A real signal may exist. A definitive interpretation does not yet. There is also the question of how to talk about the result without harming science itself. If the public expects clean answers within a single news cycle, scientists feel pressure to overpromise. If the public dismisses careful work because it is not perfectly conclusive, scientists feel pressure to underpromise. Either path damages the search for truth. The current debate around K2-18b is partly an experiment in how to communicate uncertain but genuine results responsibly. Through all of this, the planet itself does not care. It continues to orbit its red star, untouched by Earth's arguments. Whatever is making dimethyl sulfide in its air, if anything, has been doing so for as long as the planet has existed. Our job is only to listen carefully and decide what we are really hearing. That brings us to a question that should have been front and center from the start. If the signal is biological, what would the life forms producing it actually look like? Are they anything we would recognize? Or are they so strange that nothing we know about Earth biology applies? To survive on K2-18b, life would face conditions almost nothing on Earth has ever seen. The air around it would be hydrogen, not nitrogen or oxygen. The light around it would be red, dim, and weak. The ocean around it would be hundreds of miles deep, with pressures and temperatures changing dramatically with depth. If anything is alive there, it has to be tough. It also has to be patient. The simplest possibility is that K2-18b's life looks something like Earth's earliest organisms. Single-celled, microscopic, built around chemistry we already understand. About 4 billion years ago, our planet's oceans were inhabited only by tiny microbes. They had no shells, no bones, no eyes, no nervous systems. They drifted, fed on chemicals around them, and slowly multiplied. They reshaped the planet over billions of years. K2-18b might be at a similar stage, with a global ocean full of microscopic cells living in a dim, hydrogen-tinged world. These cells would have to use a different metabolism than ours. Earth life mostly relies on oxygen, sunlight, or sugar to power itself. On K2-18b, life would need to feed on hydrogen, methane, and dissolved chemicals from below. We already have examples of this on Earth. Deep below the ocean floor, in ancient rocks, there are microbes that live on hydrogen and tiny amounts of carbon. They never see sunlight. They eat chemistry. K2-18b's organisms could work the same way. The cells would also need protection from radiation, living near the surface of the ocean, where weak red light penetrates, would expose them to ultraviolet bursts during their star's flare events. But water is one of the best radiation shields in the universe. Even a few feet of water can absorb the most dangerous wavelengths. By living a short distance below the ocean's surface, the microbes would get just enough light for their chemistry while staying shielded from radiation damage. Their reproduction might be very slow. In dim light and cool conditions, life processes slow down. A single cell might take months to divide instead of hours. Over billions of years, even slow life can fill a world. If they are anything like phytoplankton on Earth, they might float in vast clouds across the upper layers of the ocean. They might photosynthesize using whatever red light reaches them. They might release dimethyl sulfide as a side effect of their chemistry, just as Earth's plankton do, in amounts large enough to fill the entire atmosphere with the gas. If the planet is thick with these creatures, the air would smell like the sea, only stronger and stranger, a perfume of life rising from a world we cannot reach. There is no guarantee these life forms exist. Even if they do, they may look nothing like the picture above. They could be radically different, using chemistry we cannot yet imagine. The point of imagining them is not to predict what they are. It is to remind ourselves that the conditions on K2-18b, while strange to us, are not impossible for biology. Earth's deep ocean vents, our underground rocks, and our acidic hot springs all host life that would have been called impossible just decades ago. Whatever lives on K2-18b, if anything, would simply be the next surprise. Of course, The hydrogen sky brings its own deep problem. Earth has never produced complex life under hydrogen-dominated air. That alone makes some scientists doubt whether K2-18b's biosphere, if any, could be stable at all. That doubt is worth taking seriously. And it leads straight into the next question. Hydrogen is everywhere in the universe. It is the most common element in existence. Almost every star is mostly hydrogen. Almost every gas giant is mostly hydrogen. Most early solar system material was mostly hydrogen, yet Earth, the only place we know hosts life, has almost none of it in its atmosphere. That is a real puzzle, and it bears directly on K2-18b. The reason Earth is so low in hydrogen is gravity. Our planet is small. Hydrogen is the lightest gas. Over hundreds of millions of years, much of Earth's original hydrogen escaped into space. What was left got bound into water molecules and trapped in oceans, ice, and rocks. Free hydrogen gas in our air is essentially zero today. K2-18b is bigger and heavier. Its gravity is strong enough to hold onto a dense hydrogen atmosphere for billions of years. That is why the planet looks the way it does. Hydrogen surrounds it, hydrogen presses down on its possible ocean, and hydrogen flavors every chemistry experiment happening in its sky. For known life, this is uncomfortable. All Earth biology evolved under nitrogen, oxygen, and trace gases. None of our familiar organisms can fully thrive in pure hydrogen. Some microbes on Earth can use hydrogen as a fuel, but they still live in atmospheres dominated by other gases. They have never had to evolve every part of their cellular machinery for a hydrogen-soaked environment. Lab experiments offer a small clue. A few years ago, researchers grew certain Earth bacteria in pure hydrogen atmospheres in sealed flasks. The microbes survived. Some even grew, though more slowly than usual. That was a hopeful sign. It suggested that even Earth-style life could in principle live under hydrogen-dominated air. But survival is not flourishing. To produce dimethyl sulfide at the levels Webb seems to have detected on K2-18b, you would need a planet covered in active, productive biology. Slow-growing microbes barely scraping by would not fill the sky with that much gas. The biosphere would have to be enormous and energetic. That raises a deeper question. Could life evolved entirely under hydrogen behave very differently from anything Earth has ever produced? Could it be more efficient in those conditions than our own microbes? Could it have developed metabolic tricks our biology never needed? In principle, yes. In practice, we have no examples to study. There is also the issue of stability. Hydrogen atmospheres can change rapidly under starlight. A planet's hydrogen sky can be partially stripped away by stellar wind over time. The lifetime of a stable hydrogen atmosphere on a planet next to a flare-prone red dwarf is uncertain. If K2-18b loses too much of its hydrogen, the cooling effect might fade, the surface might warm, the ocean might steam off. So far, K2-18b has held its hydrogen. It has done so for at least the few billion years it has existed. Whether life on it has had time to evolve, take root, and fill the sky with chemistry is a question we cannot directly answer. The evidence Webb is gathering is the closest thing we have to a vote on the matter. If life is really there, it is doing something biology on Earth has never been forced to do. If life is not there, the chemistry creating dimethyl sulfide is doing something chemistry on Earth has never been seen to do. Either way, K2-18b is teaching us about possibilities our own world cannot. But the strangeness does not end with the air. The body of the planet itself is unlike Earth in ways that could matter for life. Pressures, gravity, and depth all combine into a setting that is quietly brutal. K2-18b is a heavy world. Its mass is about 8 times that of Earth. Its surface gravity, depending on the exact size of its rocky core, would be roughly twice as strong as ours. If you somehow stood on a solid surface there, every step you took would feel like dragging your full body weight up a steep hill. That gravity is a double-edged sword. It holds the atmosphere in place. It holds the ocean in place. It also crushes everything underneath. At the surface of the suspected ocean, the pressure from the hydrogen atmosphere alone would be far higher than at sea level on Earth. Estimates put it somewhere around several times Earth's surface pressure, at least. Below that, the deeper you go into the ocean, the worse it gets. Pressure increases steadily with depth. By the time you reach the bottom of the ocean, the pressure would be hundreds, maybe thousands, of times higher than anything in Earth's deepest trenches. Earth's deepest natural pressures occur at the bottom of the Mariana Trench, where the water column above presses down at over 1,000 times the pressure at the surface. Some microbes survive there, hugging the seafloor in tiny communities. K2-18b's deep ocean may be many times more crushing. Such pressure is not necessarily fatal to life. Earth has shown that even extreme depths can host living organisms. As long as the conditions are stable, the cells of deep-sea life have evolved to match the pressures they live under. Their proteins fold differently. Their membranes are built more flexibly. They survive because they were shaped by those conditions over billions of years. If K2-18b's ocean has a stable depth, gravity, and pressure profile, life could theoretically evolve to match it. The microbes might have very different cellular structures from anything on Earth. They might rely on different molecules for support. They might grow more slowly because of the energy costs of dealing with such intense pressure. But none of these factors makes life impossible. There is also the gravity effect on body size. On a high-gravity planet, large organisms become harder to build. Bones, shells, and structures need to be much stronger to hold up under increased weight. That is one reason scientists generally expect sub-Neptunes, if they harbor life, to host smaller organisms rather than large ones. Microbes and floating cells fit naturally into high-gravity oceans. Whales and giant predators? Less so. Beneath the deep ocean, the picture changes again. The rocky core of K2-18b is huge. It may be made of materials we have only seen briefly in lab experiments. At the boundary between the water and the core, exotic forms of ice and rock could exist. These forms would not look like Earth ice or Earth rock. They could be denser, harder, and shaped by pressures so high that ordinary materials behave in unfamiliar ways. If life lives in K2-18b's ocean, it would likely never see this strange flaw. It would float in the upper layers, where conditions are more familiar. It would never know the bottom of its own world. This is the kind of detail that makes K2-18b feel almost mythological. A water world with a sky of hydrogen, an ocean too deep to map, a floor of impossible ice, and possible microscopic life floating quietly above it all. Each piece of the picture builds on the others. Each piece is hard to test directly. Yet the planet keeps drawing scientists back, again and again, because every check confirms something a little more striking than expected. That is also why this single planet was chosen so carefully out of thousands of options. The reasons reveal something about how rare K2-18b really is. Webb does not have time for everything. Its schedule is one of the most contested in all of astronomy. Hundreds of teams compete for every hour of observation time. Each request must be carefully justified, deeply researched, and judged against many others. The decision to spend a large amount of Webb's time on K2-18b was made because the planet checked an unusual number of boxes. Begin with size. K2-18b is in the sub-Neptune range, the most common type of planet in the galaxy. Studying this planet teaches us something general about a huge category of worlds, not just a single rare object. A finding here likely has broad meaning. Move to its location. The planet sits inside its star's habitable zone, where temperatures might allow liquid water at the surface. That alone is rare. Most known planets are either too close to their stars and too hot, or too far and too cold. K2-18b sits in the narrow ring where it could matter. Look at its atmosphere. Earlier observations from Hubble showed water vapor in its sky. That hint, faint and uncertain at the time, was enough to mark the planet as a serious candidate for further study. Few planets had even that much going for them. Check its star. K2-18b orbits a red dwarf, the most common kind of star in the galaxy. Studying habitable zone planets around red dwarfs is one of the great priorities of modern astronomy, because so many such systems exist. K2-18b is one of the cleanest examples available within reach of Webb. Notice the planet's distance from us. 124 light-years sounds far, but in galactic terms, it is nearby. For a target this rich, that distance is workable. Webb can collect strong, clean signals from K2-18b in a way it could not from many similar candidates farther away. Consider the planet's orbit. K2-18b transits its star every 33 days. That rapid orbit lets scientists collect transit data more often than for planets with longer orbits, where opportunities to observe are rare. Each transit is a chance to gather more spectra. Repeat transits stack the data and reveal weaker signals over time. Add to all this the brightness of the parent star. K2-18 is bright enough to deliver a strong stream of starlight, even though it is small and dim compared to the Sunday. The brighter the star, the more starlight passes through the planet's atmosphere, and the more chemistry shows up in the data. Together, these features make K2-18b a near-perfect target. Few other planets combine all of them in one place. Its potential payoff is enormous, which is why the team requested time on Webb again after the first round of results, and why future requests are also being approved. But picking the perfect target is only the beginning. To squeeze every drop of information out of K2-18b's atmosphere, scientists need many more transits with multiple cameras in multiple wavelengths. That is a multi-year project. Several rounds are already booked. The first results have arrived. The next results, likely within a year or two, will either lift the dimethyl sulfide signal to a 5 sigma detection or quietly let it fade. Either result will reshape the field. Either result will guide the next decade of telescope design and target selection. Either result will tell us, more clearly, whether the universe is full of life or whether Earth is rarer than we hoped. Until then, the team is preparing, and the next moves they have planned for Webb are already mapped out in detail. Webb does not just look at planets once, it looks at them over and over, transit after transit, stacking data until the noise washes out and the truth emerges. For K2-18b, the original team and several rival teams have lined up new observing windows over the next several years. Each one is precious. Each one could be the moment that pushes the dimethyl sulfide question past the wall. The next round will likely use both of Webb's main spectrograph systems, the near-infrared instruments and the mid-infrared MIRI, in a combined attack. Looking at the planet in different wavelengths at the same time builds a fuller picture. A real chemical fingerprint should appear consistently across multiple ranges. A fake fingerprint, caused by instrument noise or data cleaning errors, usually does not. By collecting more transits with these two systems, scientists hope to do several things at once. First, they want to push the dimethyl sulfide signal stronger. If it is real, more data will sharpen the dent in the spectrum. The confidence will climb past 4 sigma, possibly past 5. If the signal fades with more data, the team will know they were chasing a ghost. Second, they want to separate dimethyl sulfide from its sulfur cousin, dimethyl disulfide, and from any other molecules that might be hiding in the same fingerprint. Right now, the data cannot tell them apart cleanly. With longer exposure times and more spectral coverage, the line between them should become clearer. Third, they want to search for the missing companions. Ethane is the obvious one. If it really is absent from K2-18b's air, that absence has to be explained. New observations may either find ethane at low levels, fitting a slow chemistry model, or confirm that it is genuinely missing, which would be strange. Fourth, they want to study the planet's clouds and hazes. Webb's data already hints at cloud features. By targeting specific wavelengths, the team can begin mapping how thick those clouds are, how high they reach, and what they are made of. That knowledge will feed back into temperature models and tell scientists whether a cool, habitable surface is really possible underneath. Each of these tasks needs many transits. Each transit only happens about once a month. Each transit only lasts a few hours. Pulling together a careful study takes 1 to 2 years of observations, plus another year of analysis. That timeline puts the next big update on K2-18b somewhere in the next 2 to 3 years. In the meantime, smaller results will trickle out. New theoretical papers will appear. New rival analyses will be published. The conversation will twist and turn. Every few months, another headline will either strengthen or weaken the case for life. Anyone following this story carefully will need patience. That patience is part of how science actually works. Major findings are rarely confirmed in a single dramatic moment. They unfold slowly, like a long-running argument that only ends when one side simply has too much evidence to deny. The original Higgs boson discovery took decades. Gravitational waves took decades. The first black hole image took decades. K2-18b will likely take many more years before anyone claims a confirmed result. But Webb is not the only telescope humanity has. Newer machines are coming, bigger machines, sharper machines. Some of them are already under construction. They will turn their attention to K2-18b within the next decade, and they may finally settle the question. Their power will be hard to imagine. Webb is the most powerful space telescope ever built. It is also already starting to look small compared to what is coming next. Around the world, several enormous projects are nearing completion. Each one is designed to do things Webb cannot. Together, they will redefine what humans can see from Earth. The biggest of them are ground-based. Yes, ground-based. Despite all the advantages of space, modern technology has found ways to make Earth-bound telescopes outclass anything we can launch in certain ways. Adaptive optics, computer corrections that fix for atmospheric blur, allow giant ground telescopes to deliver images sharper than even Webb in some wavelengths. And ground telescopes can be enormous because they do not have to fit inside a rocket. 3 of these giants are now approaching first light. The extremely large telescope is being built in the Atacama Desert of Chile. Its main mirror will measure 130 feet across. That is more than 5 times the width of Webb's mirror. It will gather 13 times more light. It will see fainter chemistry in finer detail than any telescope in history. 2 other monsters are on the way. The giant Magellan telescope, also in Chile, will reach about 80 feet across. The 30-meter telescope, planned for Hawaii, will be similar in scale. Each one will offer enormous gains over current instruments. These telescopes will not look at K2-18b in the same way Webb does. Webb specializes in transmission spectroscopy, reading starlight that filters through a planet's atmosphere during a transit. The new ground telescopes specialize in something different. They will use high-resolution spectroscopy and direct imaging to look for chemical signals in the planet's own light, separated from the star's glare. For dimethyl sulfide, this matters. A direct measurement from a ground telescope would not depend on the same instrument quirks as Webb. It would be a totally independent test of whether the molecule is really there. If both Webb and the new ground telescopes see the gas, the signal will be very hard to deny. If only Webb sees it, scientists will continue to wonder whether the result is an instrument effect. There are also new space missions in design. NASA has begun planning a future telescope called the Habitable Worlds Observatory. That mission, if funded and built, would directly target Earth-sized and sub-Neptune planets in the habitable zones of their stars. It would search for biosignatures across hundreds of worlds, not just one. K2-18b would almost certainly be on its list. Other agencies are working on their own concepts. The European Space Agency is planning a mission called Ariel, set to launch in the next decade. It will study the atmospheres of around 1,000 exoplanets. It will not focus on biosignatures specifically, but it will help map the chemistry of the entire population of planets in our region of the galaxy, providing context for unusual cases like K2-18b. Each of these projects will take years to deliver results. The first new ground-based observations may come within the next 2 to 3 years. The first major space mission upgrades may come within the next 10 to 15 years. A complete answer on K2-18b may take that long. That means the story is not going away. It will keep developing, year after year, telescope after telescope, until one of two things happens. Either we confirm life on this faraway world, or we fully explain how non-living chemistry made the signal. Either result would be enormous. To grasp why, think about what a confirmed detection would actually do to our species. Imagine waking up one morning and learning that scientists have officially confirmed life on a planet around another star. Not bacteria buried in a meteorite, not strange chemistry on Mars. Real, ongoing biology, breathing chemicals into the sky of a world more than 700 trillion miles away. The moment would be unlike anything in human history. Every culture, every religion, every philosophy would have to absorb the news in their own way. Some would see it as proof that life is common in the universe. Others would treat it as a sacred event, a shift in the order of things. Schools would change their curriculums. Books would have to be rewritten. Children would grow up assuming, from a young age, that we are not alone. The scientific impact would be the most direct. Astrobiology, the study of possible alien life, would jump from a small specialty to one of the biggest research fields in existence. Funding would pour in. New telescopes would be designed specifically to study other inhabited planets. Universities would build entire new departments. The number of people working on the question of life beyond Earth would multiply within a decade. The cultural impact would be just as deep. Movies, television, novels, and games already imagine alien life all the time. A confirmed detection would change how those stories are told. Aliens would no longer be only fiction. Audiences would think about real life forms, in real oceans, on real worlds, while watching imagined ones. The entire sense of what is possible would shift. The philosophical impact would matter most of all. For most of human history, we have wondered if we are special. The idea that Earth is the only place with life has shaped religion, art, and self-image for thousands of years. Confirming life elsewhere would not destroy that sense of meaning, but it would reshape it. We would be one example among many, not the center of creation, but part of a larger family of worlds. The political impact would be quieter, but real. Space exploration would gain new urgency. Nations would compete to build the next telescopes. International cooperation around astrobiology would likely deepen because the search for life is too large a project for any one country. The scale of the goal, identifying living worlds across the galaxy, would push countries towards shared work. There are also practical questions. Would we try to communicate with K2-18b? The simple answer is that we cannot. Microbes do not receive radio signals. Even if we sent messages, they would take 124 years to arrive, and another 124 to bring back any reply, assuming a reply could even come from organisms with no language. Confirmed life on K2-18b would be a profound discovery, but it would not be a relationship. Still, knowing that life exists out there would change everything about how we look at the night sky. Every star would feel different. Every distant point of light would carry the possibility of biology. The universe would feel less empty, even if the distance between us and our neighbors remained as enormous as ever. The discovery, if it comes, would not give us answers. It would give us a new question. A question that has waited inside human thought for thousands of years. If life exists in two places, how many places does it really exist? How common is it? how fragile, how ancient, how varied? That question would shape the next century of science. And the answer, when it comes, would change what it means to be human. For most of recorded history, humans have wondered whether other worlds have life. Ancient Greek thinkers debated the possibility of countless inhabited spheres. Medieval philosophers argued about whether alien souls would need salvation. Modern astronomers built telescopes specifically to search the heavens for company. None of them had real evidence. Every generation guessed in the dark. If K218b's signal turns out to be biological, that long question shifts from philosophy to data. Think about what that shift means. Today, we assume Earth might be unique. We assume that whatever made life appear here was probably special. The idea that life is rare in the universe shapes how we think about our own origins, our purpose, and our future. It also shapes how we look at our planet. Earth feels precious because it might be the only place where life ever bloomed. Now imagine the opposite. Imagine life on K218b is real. Imagine its atmosphere is full of chemistry that could only come from biology. The implications would not stop at a single planet. If a planet so different from Earth, with hydrogen skies and red dwarf sunlight and crushing oceans, can host biology, then biology may be common across the galaxy. The conditions that allow life would not have to be exactly Earth-like. They would just have to allow water and basic chemistry. And those conditions exist on countless other worlds. That single conclusion would reshape almost every assumption in modern astrobiology. The galaxy would not be a quiet, mostly dead place with one strange green dot. The galaxy would be a sea of possibilities. Each one of the billions of stars in the Milky Way would be a question. How many of them have planets with life? How many have liquid water? How many have produced anything more complex than microbes? The question would also turn inward. If life is common, then we are part of something much bigger than just our own world. Earth would no longer be the exception. We would be one example out of many. The same chemistry that gave rise to us would have given rise again and again on other planets, around other stars, across distances we cannot cross. We would join a family we have never met. There is also a darker question that comes with that idea. If life is common, but intelligent life is silent, where is everyone? This is the famous Fermi paradox. The galaxy is old. Stars are old. Planets are old. Even if intelligent life is rare, it should have appeared somewhere before us. So why have we never heard from anyone? K218b's signal would not solve this paradox, but it would sharpen it. If microbial life is common, then the silence we hear is even harder to explain. Maybe intelligent life is much rarer than microbial life. Maybe civilizations are short-lived. Maybe distance simply prevents contact. Maybe we are the first, or among the first. In this corner of the galaxy, these questions would not have clean answers, but they would change how humans think about themselves. Imagining our place in the universe would no longer be a matter of fantasy. It would be a matter of serious scientific work. The night sky would become a working map, not a mystery. For a species used to feeling alone, this would be a profound, even uncomfortable, shift. We have built our myths, our stories, our religions, our heroes around the idea that Earth is the place where the universe became alive. Confirming life elsewhere would not erase those stories. It would simply add new ones, stories of other worlds, other oceans, other quiet beginnings, happening at the same time as ours. That is why a single dot of light twinkling in the constellation Leo may end up carrying a heavier meaning than its size suggests. Through a backyard telescope, K2O-18 is barely visible. It looks like a faint speck lost among brighter stars, easy to miss unless you know exactly where to point. To the naked eye, it does not exist. The light from its planet is even fainter, a tiny shadow inside the star's already dim glow. Yet scientists have learned to read that shadow. They have measured the chemistry it carries. They have spotted the fingerprint of a molecule that, on Earth, only living things make. They have done all of this from 124 light-years away, using a single telescope shaped like a flower of gold. The story of K2-18b is in many ways the story of how far human curiosity has come. A few centuries ago, we did not even know other planets existed beyond our own solar system. The first confirmed exoplanet was found around a regular star only in 1995. Today, more than 5,000 have been catalogued. Tens of thousands more are likely waiting to be found. Each one has a story. Each one is a chance to learn how planets behave, how atmospheres form, how chemistry plays out in worlds nothing like ours. K2-18b is one of those stories. It is the first to come this close to a confirmed sign of life. Whether or not that signal holds up, the planet has already changed astronomy. It has shown that Hycean worlds, or something close to them, exist. It has shown that Webb can read alien atmospheres in stunning detail. It has shown that humanity is now capable of seriously asking, and possibly answering, the deepest question we have ever asked. Are we alone? The answer is not yet in. The signal might fade with new data. The molecule might turn out to be something else. The chemistry might turn out to be exotic but lifeless. Or the signal might grow stronger. The molecule might be confirmed. The chemistry might force scientists, slowly and carefully, to admit that biology is the most natural explanation. Either path teaches us something we did not know. That is the quiet beauty of the K2-18b story. There are no losers in this experiment. Every result is a step forward. If life is real, we have crossed the greatest threshold in our species' history. If life is not the cause, we have discovered something equally valuable. New chemistry, new processes, new things the universe can do under conditions Earth has never tested. The team behind the discovery, the rival teams that challenge them, the engineers who built Webb, the technicians who keep it running, the students writing the next theory papers, all of them are part of a larger human effort, an effort to look outward and see what is really there, rather than what we wish were there. That effort began with the first early astronomers and continues today, with millions of people across the world who follow each new finding with curiosity and patience. K2-18b is not the end of that effort. It is one important moment in it. There will be more planets, more atmospheres, more strange signals, more debates, more discoveries. The galaxy is enormous. The stars are countless. The chances for surprises are endless. If, in the next 10 years, the dimethyl sulfide signal is confirmed and rises past 5 sigma, then a single tiny dot of starlight in the constellation Leo will become the most famous point of light in human history. It will be the place where we first saw life beyond Earth. School children 100 years from now will know its name. Spacecraft, missions, novels, and dreams will be built around it. If the signal fades, K2-18b will still be remembered as the planet that got us closer than ever before. The world that taught us how to listen carefully to a faraway sky. The world that proved we have the tools, the patience, and the courage to ask the largest question imaginable and to actually wait for an honest answer. Either way, the story is far from over. It is only beginning.